Hello everybody and welcome to Handmade Hero Show. We code a complete game live on stream. We are doing some KD tree stuff, and this is really just because we want to make sure our lighting runs as fast as possible. And I had also some ideas for that. Looks like we're booting here for the first time. I had some ideas for that, and I kind of wanted to try some stuff that I thought about in terms of reducing the variance in our code currently, like in our lighting solution, because it looks pretty good, but it's got a little flicker to it, which I don't actually mind as a effect, but I kind of wanted to know to what extent we could make it more solid. And I had a really good idea about how I think we could do that. And so in terms of looking at our lighting, again, like I have an idea I want to try for that. I think I just want to keep on the KD tree thing this weekend just because we had started last weekend and I'd like to finish it. So I think what we're going to do today is just take a look at implementing that KD tree loop that we sketched out. And then from there, probably that'll take us all weekend, unfortunately. And then from there, what I'd like to do is probably next weekend try a little bit of the thing that I was thinking of before we start optimizing the KD stuff. Because before I forget what I wanted to try, I wanted to put in a little bit of an experiment there where we take a look at what we can do in terms of reducing the lighting variance that we get from our lighting. So I'm going to take a look at that and see what happens, and we'll go from there. So we have our routine sketched out from last time where we had our raycast, and we were sort of talking about how are we going to do a KD tree traversal here that's more direct and like less about just sort of shoehorning it in. When we put it in originally, we just kind of shoehorned it in, and this is the original up here. That's the one that's running right now. And then now we've got this sort of other one here that we sketched out that's like, okay, this is how we think the KD tree might run. And it's kind of confusing because there's a lot of ways we could structure this, and it's unclear really. So we'd kind of, I think, just have to like implement one and then sort of like push forward on it, because I don't know that there's any way to really like intuit up front exactly how this should work. So if you take a look at how this is going, what you can see here is we're expecting to do something where we pull something off a stack. We look to see whether or not we need to test it for collisions. If we do, then we loop through and actually test it for real collisions of the ray with our boxes. And that's just a loop through all of the child leaves, right? Then after we're done checking all the child leaves, then we hunt back up the stack to see if we can find anybody who we haven't processed yet that still needs to be processed. And the reason that I say still needs to be processed is because when we find an actual collision with a box, which we're doing inside this leaf testing here, as we look at the sides that we've pushed on the stack that we haven't tested yet, we know that if we've already found a hit on our ray that's closer than the closest box could be because of the plane division in the KD tree, then we know that we don't actually have to do that test, right? We don't have to walk down that side of that tree. So this end side bit here is sort of the early out that says, look, if this is not true, meaning if at least one ray is not on the other side of the KD tree separating plane that we're looking at, then we don't have to continue. You know what I'm saying? Now, we do have a bunch of issues we have to work out here because we have to make the math work out, right? And we'll talk about that in a little bit, but that's basically what we're talking about. And what you can see here is the other side of things where we're not doing a leaf container. So again, this is just what happens when we've bottomed out, when we've gotten all the way to the bottom of the KD tree, and we are testing the actual boxes that are contained in the node, and then we're walking back up the tree to see where we should start descending next, right? So that's what this branch does. This branch is when we were when the thing we pulled off the stack. And it's not really off the stack because we like I said, we changed the sort of recursive pulling off of the depth stack to being something we only do when we finish with the leaf. Because we know we're just going to descend down all the way to the bottom when... I'm not explaining this well. We know that we need to go all the way to the closest thing in the KD tree first, and then we want the next closest thing, and the next closest thing, and the next closest thing. So when we descend, which is this side here, because this is what happens when we don't handle a leaf container, we don't push the things on the stack here that we're going to test immediately. Instead, we just take them as our next stack value to use. So we just take it immediately. The only time we start pulling things off the stack is when we've bottomed out, because now we can't go down anymore. So now we just pull something off the stack to figure out, okay, who should we test who's like above us, right? And so that's what this part does here. Now, I think... I haven't thought about it too hard, but in theory, because we know what side, we always know how to classify ourselves relative to one side or another of a KD tree. In theory, we could also do this traversal stacklessly, because, and we may want to, because if we know that we can always just do a piece of math that's relatively straightforward, like maybe it's actually fairly quick to do, we could actually get out of the branching altogether for putting things onto the stack in the first place. Now, I don't actually know that we're ever going to have to worry about that, because with this new tree structure, we could conditional move these on there, and because we're no longer pulling things off of the stack immediately anymore, those C moves might actually just work. Now, I don't know that that's actually true, but I think it probably will be. And this right here, where we take the cur stack value that's going to be used next time, that's actually the one that's going to cost us the most, I think. Because the next loop is going to be completely dependent on that finishing either way. So the fact that it doesn't come out of a stack doesn't really matter. That's going to be, this as a conditional move or a conditional is really going to be the part that we probably stall on either way. But ignoring all of that, like I said, this part here can probably just be two conditional moves now, because we won't be looking at it for a long, long time. So those C moves can probably just happen, and they probably won't cost us much because nobody's dependent on them at all. The next time anyone could even think about looking at them would be after going through this entire loop and testing at least a few boxes, and then getting in here and starting to pull things off the stack, right? So because there's so many intervening instructions here, you know that you're not going to line up people serially dependent on this thing until after it's probably a completely known quantity, would be my guess. I could be wrong about that. So I don't think there's going to be much of an issue there. But I could totally be wrong. But that's the basic sketch. And so if you look at the things we need to actually do, I think one of them is just correct already. Like, we'll scrutinize it a little bit, but I think one of them is just correct already, basically. And the other one is the one that we actually have to probably do a little bit of engineering on, because I don't think it's quite right. So if we take a look at what goes on here, when we're actually processing a node in the KD tree that is not a leaf, so it's an interior node of the tree and divides the boxes we have into two halves, one that are on one side of the split plane and one that's on the other side of the split plane. The thing that we need to do first, and the slowest part that we have, like I said, I don't really know if maybe there's smarter ways for us to do this, but the slowest part that we have is this part here. Now, one thing that I'm not sure about, in fact, I think we could do this much more efficiently than we're doing it here, and actually we probably just should. So if you look at what has to happen here, you can see that we're effectively doing like masking operations. And I think we probably don't need to do those here. Like, the reason we're doing this, so you can imagine this side where we're talking about the ray direction. there are 4 different ray directions that are, slightly different. And that's because we're casting 4 rays at a time, right? And if you look at what's going on here, we need to produce a X, Y, or Z value from these ray directions. So we need to select just those components out by using the masks here to produce a vector that's just the X's, just the Y's, or just the Z's of our directions, right? And since we don't know which one it is, we're doing it this way, right? Now, there's other ways we could do that. Like, we could do that as a load, and in fact, yeah, the more I think about it is, why aren't we just doing that as a load? So I think this code is dumb, and before we go any further, I'm just going to replace it with something that I think might not be as dumb. Don't quote me on that fact, because it may still be as dumb. But yeah, I'm just going to go ahead and say that I think that's probably a little bit dumb. The reason I think that's a little bit dumb is if we take a look at the v34x struct here, so I'm just going to look up the actual structure. What you can see about how this is actually created is it's just X's, Y's, and Z's anyway, and here's the E3 element accessor, so we know that they're sequential in memory. So I'm gonna say, like, can't we just do a 128-bit load with an index, and we know that index is low? Can't we just do that and not have this problem? So, meaning, instead of this, if we actually just do this as a load of the ray origin using an index, I mean, can't we just do this? So if we just take the dimension index of this box, like, or like, the k dimension index, like the thing we split, or maybe it's called a KD index, the axis we split upon, we shouldn't actually have to do those masks because we can just do one 128-bit load of the value. And since we're loading those 3 values from that cache line, they'll all be packed together. We should hit the cache line every time. It should be an L1 cache hit, and we should just be able to do a load directly. So I don't think we need to be doing sequences of operations to do the mask, because I don't think there's any reason we can't just load it directly out. So similarly, like here, where we do this, I think we can just, I think we can just load that, and I don't think we will pay a penalty for it. Now, this wants to be done slightly differently. Instead of actually doing the ray origin part here, what we want to do, again, is just do both loads and then the add, right? So we want to load the start and the end, and then when we do our hit P, we want to just add those together by doing the add of just the components, right? So I don't really know why we did it the other way around. It's way more expensive to do it that way, and probably we were just not thinking about that part yet. We were just kind of sketching things out. But now that I'm like looking at it more closely, like that seems more standard to me, right? So this is like start D and end D, right? And then the place where this thing would end, like the place where this ray would actually end, is now just going to be, if you did the hit P, it's just going to be the start plus the end D, right? And this is actually, sorry, this is, I should say dir D, right? So this is the ray direction. So all we're doing is, instead of actually computing the actual endpoint, we're just computing one dimension of the endpoint, because we know that the split plane is dimensionally aligned, so we don't have to test Y and Z. We can just test X if it's an X split plane. We don't have to test X and Z if it's a Y split plane, right? So start D and dir D here, right? We combine those two together, and we end up this T-ray value here this is now just a scalar multiply, and we end up with whatever the hit P is for this particular dimension. And then what we can do is say, well, whatever the actual plane D value was here, again, we can subtract that out as well, and then we can do our test on it. So to do that, like in here, we could probably just add that in. So if we want to, we can just do something like this, right? And then we can just see whatever the hit P, or I should say this is the end P, right? And maybe we call it ND, because that makes more sense. So here we can just do a move mask out and take a look at what the end sign bit is, and then we know. And the reason that this is not quite right, as I said, is because we don't know which side we're looking at here. So there is a little bit of an issue. We could take this value, the plane D value, we could try to figure out something to do there. And it's possible that we could do that on the push side of things. So, you know, this is the one part we've got to figure out, is how are we making this end sign bit thing work, right? So we could imagine having some piece of information here that tells us, I don't know, but this end sign bit, when the move mask comes out, what we're going to end up with is we're going to end up with a mask, like it's going to be, you know, 0, 1, 1, 0 or something, and it's going to be ones in the place where it was on the positive side of the plane. So for each lane, for each of the 4 lanes, we're going to have 1s on the positive side, 0s on the negative side. But the question is, which one do we want, right? So if it's a mix, if it's 0s and 1s mixed together, then we always need to do it, because that means somebody, at least one of the rays, actually doesn't early out. But the thing we have to know is if it's all 1s or all 0s. We don't know whether we do or don't do it, right? So the thing we have to disambiguate is if we pushed on the positive side, right? Because we're going to descend down one side, negative side, positive side. We're going to push the opposite side. But we don't know which side we pushed, right? So what we're going to have to do in the start side code, so here where we push these on, we're going to need to push on a value that tells us something, right? Some piece of information that we can use so that we know which way to test this thing, right? And that's the tricky bit. Now, there's 2 ways to do it. One way is to always do the test the same way and to add a multiplier in here. So, for example, if we pushed on a 1 or a negative 1, we could load out of the stack the 1 or the negative 1 there, and then we would multiply this result, ND, by the 1 or negative 1, and off we would go, right? Now, that doesn't seem like a very good idea to me, because it requires us pushing probably more information on the stack than we need. Because, I mean, to store a 1 or a negative 1, we only need 1 bit, right? So we should be able to stick that bit value into our stack in a way that's more convenient, so that our stack can still be just 32 bits wide and not have to store entire floating point values for no reason, right? So I'm assuming that we probably want to do something smarter than this. And like I said, I don't actually know that that's true, but I'm assuming. So what I want to do is think for a minute about what we would store, and maybe I'll go to the Blackboard for this, which I have to like reload because since we did a separate stream, I had a separate Blackboard up. Turns out I didn't actually need it because I had enough diagrams last night when I was talking about graphic novel prepress. But so let me try and open here a Milton canvas, and I don't even know where this thing is, but I think it's in archive. Here? Does this look right? This does not. This looks like, I don't know where this is. Hold on a second. This looks like not recent. Day 420. All right. Day 433. Like, this doesn't look recent. This looks like it's off somehow. Day 469. I don't know what that just did. I accidentally drew into it. So, wait, that's where the Milton canvas was, I thought. So, what's the deal? All right. Maybe our canvas has gotten destroyed. I have no idea what happened. I tried to switch last night, and I did not understand what occurred at all. It was very unintuitive. I feel like probably there should be a different way that this works, because I don't understand what it means to save a Milton canvas. Like, when I close it, I don't know what it does. You know what I mean? Like, I don't know where it saves it to. So I'm not sure what's going on here exactly. So we're just going to go up to the top of this canvas, which may or may not have ever been saved. And honestly, I wonder if that means this whole time it hasn't ever been saving our canvas. It like saved it to some temporary file that we don't even know about or something like this, which could be the case. I don't know. I really just don't know. I have no idea how Milton works at all. In fact, maybe we'll just create a new canvas because I just don't even know what that means. All right, it doesn't look like I can do that because it resets all my settings. I really just don't know. I don't understand. I think there probably should be some like thought put into how that system works because it doesn't really make any sense to me. All right, so let's move over here a bit. And we'll just start again. That kind of sucks if that's the case, because I've thought that I've always included the canvas, the Milton canvas, with the distribution. It gets packed up in there. But I guess if that's the case, then I haven't been since like day 433, because it just hasn't been saving it, I guess. It just saves it to some temp file that I don't know about. And I have to manually tell it to save it or something. I don't know. I'm super confused right now. If anyone understands Milton at all and wants to tell me, I'm happy to try and fix it, I guess. But also, you know what I just realized? We don't have our little overlay on either, do we? But this whole day has been a bit of a disaster here. We are 5... I don't remember what we are either. $5.95? Nope. Going the wrong way. There we go. Okay. So yeah, I don't know if the Milton canvas has been destroyed. It may have been. That's okay. My handwriting is so bad, no one's ever going to be able to read it. But the point is, let me explain what I'm talking about here in terms of side bit masks. So what's going to happen is we've got a KD tree split plane here, and we've got array, and it's on some side, and it goes in some direction. And what we're going to do is we're going to produce another point. And remember, we're doing this 4 wide. So there's actually, like, it's more like this is happening. And so we're going to produce 4 points, and some of those points are going to be on one side, and some of those points are going to be on the other side. Now, in a particular direction, let's say we're using the x-axis here, there's the negative side and the positive side relative to the plane. And since we subtract away the plane D value, which is this, we're going to have negatives for everyone on this side and positives for everyone on this side. We're then going to do a move mask to move out of the vector registers just the sign bit of those four floating point values, and we're putting those into a general purpose register. That's going to leave us with one of 16 possible combinations, right? Like 1001 or 1011 or 0101, right? And these correspond to the signs of, like, basically which side these are on. So anyone who's on the positive side is going to get a 0, and anyone who's on the negative side is going to get a 1. I believe. We can double check that. But I think it moves the sign bit, and I think the sign bit is positive if is 1 if it's negative and 0 if it's not. If that makes sense. But either way, we can obviously verify that, so if we're wrong about this, doesn't matter. Point being, we know that we're going to have a bit value in here that corresponds to which side of the plane it's on. Problem is, we don't know which side we want to actually measure. We know that in the place where we actually determined which side the start was on, that as we descended the KD tree, we did push one side or the other. So we know which side we want it to be. So what we need to do is when we do the push, we need to record something that tells us which one we're going to do, right? If that makes sense. And in order to push which one of these we're going to do, we need something that will go from this to like a yes or no value, right? That's whether we need to descend. So what we're trying to do is determine whether any of the rays are on the far side of the plane. So in other words, there is going to be, oh, and that's your answer right there. So as I'm saying it out loud, I realize exactly what the answer is. The answer is it's just equals, is what we need. What we need to push on is 1111 or 0000, and all we need to do is say if it equals one of these, or I should say not equals one of these. So if it's not equal to the pattern that we push, then we have to use it. So that's actually what we're going to do. Yes, yes. Oh my God, everything is so tangled. I hate having to have a streaming setup. It's the worst. There's so many cords. It's a disaster. There's like 12 pairs of headphones. Never stream, folks. It is going to be so nice when I don't have to stream anymore. Okay. It's like such a disaster. If you have OCD, you can't stream. Like basically that's the thing you should know. Okay. So anyway, if you take a look at what's going on here, that should basically give us what we need to know. We're going to have to say, look, in any case, if there's anything other than exactly the one pattern that says we've early outed, then we're going to have to continue. So this is basically a not equal to some stack match pattern. So this cur stack value thing that comes out here is actually going to be sort of a composite. And so we're going to want to do something like this, where we do the stack push. The cur stack value here, this U16, that is actually the correct thing, but the stack itself is not going to be a U16. So what's going to happen here is when we record this cur stack value, when we push the box stack on here, what we're going to do is when we push this on, this will push a 32-bit value that's properly encoded because we actually did look out the sides. And then on here, when we pull it off, we're actually going to get a like stack value or a stack, a packed stack value here. And then the cur stack value is going to be the packed stack value, probably ANDed off. And then the stack match pattern, right, or the plain test pattern, maybe let's call it that, is just going to be masked off of there, right? So the plain test pattern in this case is going to be whatever the cur stack value is, and it's going to be shifted down by the 16 bits. So we're going to like slide it over, right? Now, there's two ways we could do this, and I'm thinking that maybe this is the wrong way. So I'm thinking maybe what we do is, since we know we always have 4 match values, we're going to go ahead and slide those this down, and then we're going to AND this with OXF to get those out. So I think that's probably more what we're going to do, right? So we're going to do a thing that looks something like this. Oops. And then the plain test pattern gives us exactly what we need to know. So that's it. Now I want to say that's actually the entire code. Actually. We now no longer need this. So that's gone. So really the only thing we need to store in the lighting boxes to support the KD tree is we need the plain D value and the KD index right? Something like this. So there's which dimension we're using. We would load that out. There's the plain D value, which we need to load out. And then I guess there's the two sides, and that's it. So if we take a look at the lighting box structure, which is that, if you take a look at how that's used, really what we're talking about here is just this top part would get fussed with, right? And that's if we want to store them in line, which I don't know that we need to do anymore. So I think we can probably get out of that business entirely and just store this exactly. So in the lighting code where we actually create the tables and all that garbage, I think what we can probably do here is say, let's just have a table that we're going to use that has all of the has all of the KD tree stuff in it. That's what I think we would want to do. Now, the tricky part here is that if we actually want to do that, we do have the problem of looking up into two separate arrays. And so looking at the light box, which is here, we have that problem that this pack structure, right, is the thing that tells us that piece of information. So I'm going to go ahead and say that probably we want to figure out a way to do this loop without checking that. So I'm guessing what we want here is to put the leaf container flag into something saner. So I'm going to go ahead and say something like this. And I realize I don't really know what I'm doing exactly here, but let's say that we have is leaf container, and it's a separate thing. So we just know what it is. When we are going through here and picking things off of the stack, it probably is fine for us just to use one additional bit for that, right? And so, for example, like maybe it's something more like this. So whenever we push something on the stack, we actually know which one it is or something. And so we can actually just find out what is leaf container should be by shifting it and masking it off, right? Now, because this leaf container is just going to be used as a Boolean, I'm going to go ahead and say we probably don't even have to do that. We don't need it to be 0 or 1. It can just be non-zero, and it will be fine. So I think if we do this, that's the entire decode, and we no longer need to actually have isLeaf container encoded in here anymore. So that would go away. So like, for example, so we don't want to remove it yet because I still want to be able to test against the old version of these routines. So I'm not going to vape that code out and put like, you know, the new path in yet as mandatory. So we're not gonna do that, right? So yeah, just to keep that in mind. What I do want to do, however, is we have to think a little bit harder about how we're gonna run these tests now. Is this how we are typically running this, I think? Yeah. So we do need to think a little bit harder about how we're going to run these tests now, though, because I need somewhere to put the KD box information, and we need that to be something that the Lightning code can actually work with. I think what I'm going to do for now, again, is just sort of take advantage of some facts here that we know we can use. So if I were to union this in here, like so, and I'm only doing this so we can still flat load the structure from our old data files. That's all I'm doing because I want to keep that load in place. All I'm doing here is just saying, look, we had this before, overlaid on top of it because we don't need that anymore. We're never touching it and aren't going to use it. I'm just going to lay in the actual thing we need here, which is the KD tree count and like a KD tree node, right? Something like this. And so what we'll do is we'll figure out how many of these we might have maximally. We'll have an array there that we can use as scratch base, so we just build them in there and then off we go. And then we can have like literally a KD tree node here for lighting that we can use, and that KD tree node will just literally only have exactly the things that we need here. So it needs the plain D, it needs a U8 for the KD index, and then it needs the two sides, right? So it needs basically this. Now, I don't know that it needs anything else, and as far as I can tell, this KD index is probably not actually something we can store as a U8, because, I mean, yeah, there's just a bunch of extra padding there. So it probably looks more like that. Yeah. The good news is, if I'm reading that right, this is actually like 4 by 4 or 16 bytes, right? So in other words, we've got two U32s for the side, so that's 2. We've got a plain D, which is an F32, so that's 3. And then we've got 1688, which is another 32 bits. So that's 4 32-bit values, or 4 4-byte values, or 16 bytes total. That means 4 per cache line, which is a nice, compact structure. So again, the reason that I would just point out that I kind of like that better is because if you take a look at how much memory traffic we were going to have when we were using the lighting box structures, well, if you look back at the lighting box structures, how many things are in there, you can see that there's a 32-bit value here in the lighting box pack, so that's 4 bytes, but then we have 3 times 3 times 4, so that's, to write out the entire equation, right? We've got 3 V3s, which are 3 4-byte values, plus 1 4-byte value, or 40 bytes per, right? Which I believe is how big this is. So 16 per node is a lot better than 40 per node for obvious reasons. It's more than twice as large if it's at 40. So in terms of the total amount of stuff we're moving through the routine, if there were any cache issues we were having, this would definitely have helped them. Now again, we're doing this to do less ops here as well. So we haven't really measured the cache effects. We're just trying to simplify the ops we're actually doing for what we have before we start optimizing. So unfortunately, we're not going to necessarily know how much the cache affected us here, because we're also going to be doing less ops, right? So sometimes you can't, yeah, I mean, it's hard to really know exactly how good that would be. We could try to look at some cache performance counter values, but again, because we're changing the ops at the same time, I'm not sure to what extent we could really make a firm statement about that, because, you know, who knows what'll happen. We don't even know if this is going to be faster. It could be slower, right? So what we want to do here is say, okay, when we're getting this stuff out, we actually don't grab the box early on. In fact, what we're mostly going to be doing is looking more specifically we're going to be looking more specifically at individual values and how we're going to pack these in. And so actually, you know what? It turns out that there might be a real good reason. Oh, you know what? There is. Okay, cool. There's a really good way that we can actually use these K-tree nodes because of what we're going to have to do in here. Okay. So actually, this is fine. We're going to need this, right? Because we're actually going to need the leaf count and the first leaf index, right? Now, we could just snuggle those into the sides because we know that we're not using them, but we might as well just use the two values we actually had for the padding because there's no reason not to, right? So yeah, turns out we can use those and you know, it's all good, I think. At least as far as I can tell, that seems right. Yeah. Okay. So yeah, what we would do now is we'd always load KD tree nodes here. So we'd actually load a KD tree node out of this thing. And we'd always load those out of like KD nodes, and it would come out using curstack value, right? Then what we would do here is we want to load out the information we actually need. And in this case, I don't think we actually need to do it this way because there's no point in actually loading it out anymore. We can actually just use it when we actually need it because you know, they don't get reused. It's pretty clean actually the way we're doing this from what I can see. So we'll load up that here. The KD index will load here, like so. What do we call that? Just KD index. And then we also would load it here. Although here we actually only need it once. So it would literally just be in there, right? And there. So yeah, I don't think we've really addressed this yet. When I said I think that's finished, I don't actually think it is. We probably have to take a look at that a little bit more carefully, but we'll see. So yeah, I think that's all we need. So then instead of looking at say like box pack and this nonsense, right? We would just use first leaf index, and we would look off of the KD node here. Since I kind of been doing it this way, maybe we'll change to doing it like that. So for the leaf index, we go first leaf index like so. Pretty sure the rest of this routine stays the same. And then in this case, we can actually just have a stop value here. So this is going to be like while leaf index is less than 1 past last leaf index. And we're going to generate that value up here as an unpack operation. So 1 past last leaf index is just going to be the leaf index, which is the first one, and then the child count, right? So the KD arrow leaf count. So we unpack those in the case of a leaf container, we loop over all of them, and we stop when we get to the last one and end out, right? And then we could actually shove that in there for good measure if we wanted to. I don't know that we do, but we could. So we can then look at this part of the routine. That all looks fine. It's using the packed stacked values here to extract what we need to extract out of those. And doing the test, then it knows whether it's a leaf container or not, obviously, as necessary. And I suppose this actually looks like this. So we set curse stack value to 0 because we have bottomed out. We look up the tree to see whether or not we can find a new one. If we do find a new one, we break out and off we go. Otherwise, we don't. And we just leave it at 0 when the depth bottoms out. Yeah. I don't know. Probably not the best way to write that. I have to think about that a little bit more. But it's something like that. Okay, so on the other side, when we're actually processing a node for the first time, what we do is we say, okay, which side is the origin on? And this right here is going to give us that piece of information. And so we could actually just say, look, it's whatever the origin actually is, minus the plain D. We don't really need to belabor that point. We're going to move the mask, and we're going to AND it with just the bottom bit to give us a 0 or a 1 value, right? Then what we're going to do is say, all right, whichever side we were on, so from the 0 side to the 1 side, we're going to push that on. And, I'm sorry, we're going to descend to that side. And then on the box stack, we're going to push whichever one we didn't do, right? Now, if we do want to do a C move here, again, I'm not 100% certain about what this will look like. But let's set it up to do a C move for now. So we know that MSVC won't generate C moves, even if it probably should. So I'm going to just say, like, the box stack at value, you know, is this thing. And so we're going to take the box stack value as a reference here. That's where it would get pushed on. And then we're just going to say, we're always pushing something on in this case too, so I can do the increment there, right? So we don't need to C move that. So this will C move. Oh, wait, what am I talking about? I'm ridiculous. We got rid of the conditional. It's not a conditional. It's just a different address for load. Great. Never mind. I'm still thinking C move. We don't have C moves anymore. No issues. Oops. Get rid of that. Awesome. So we don't actually do any conditional moves here. We just do moves. They're just straight moves, right? With a different offset. So it's just an address load thing. Perfect. Okay. I think we're good. I'm sure there's so many bugs in there I can't even imagine, because this is very complicated. But I think that is the end of the bugs my brain can find. So now we have to do the unsavory process of finding all of the bugs my brain didn't find. And in order to do that, we're going to have to first start by introducing a bunch more bugs, because we now have a different format, right? Then we are, like, we're not storing these KD nodes as KD nodes yet. So in the split box routine, we need to be able to write those out. You know what I'm saying? So the way I would like to do this is, if you look here, Splitbox always has two routines here, right? This is what happens if it actually split the box into two, and this is what happens if it didn't actually split the box into two. And so we should be able to create both trees side by side so that we can still run both versions of this code. And that should be pretty straightforward, I think. Don't quote me on that. So when we actually run the split box routine and we're passing a lightning box down, so you can see like how this works, right? It adds some storage, then calls split box and says, here's the box that you're actually working on. What we should be able to do now is also pass in here, in addition to the parent box that we're working on, we can pass a parent node. So we'll just build both at the same time. We'll call that, I guess, parent KD or something like that. And that way we can actually set these up properly. So what we know is if we're working on one of these parent KD things here, and this is possibly going to be a little bit more complicated. So if we actually split, we're going to need to do, if we didn't actually split, then we ourselves are a leaf container, right? If we didn't split, then we aren't. So what we need to do here is we need to know some additional information. Like, for example, when we return here, we're going to need to return the actually split value so that we know which one our children were, right? Like if they're leaf containers or not. Now, we don't need that for the current system, but we do need that for the new system, because we load up the sides value, the two sides values that are packed into our parent, those side values encode whether the person that they are referring to is actually a leaf container, right? If that makes sense. And that's to avoid us having to pack more values in the stack, which maybe we should do. Oh, man. Now that I'm thinking about it, I'm thinking maybe that's actually something we should just do. Yeah, we should. Never mind. Forget everything I just said. Every time I say that, I think about, there's a Key and Peele sketch where they're at like a diner and they're each trying to outdo each other about how, like, it starts off with how like authentically Southern their order is going to be, like how true to their roots the order is going to be, but it quickly degenerates into them just being absolutely ridiculous with their orders, as most of those kind of Key and Peele sketches do. And at one point, like when they're really heated, and I can't remember if it's Key or Peele actually. I need to go watch the sketch again. It's been too long. One of them goes like, forget everything I've said up until this point, to like erase all the previous order, and then goes, to order something absolutely ridiculous. I need to watch it again. Like most Key and Peele sketches, it's very good. They do that sort of escalation kind of comedy where each one is trying to up the other one in like a sketch, like better than anybody else. It's so good. They have so many of those. They have the like facial hair at the office one. They have the hats where they do the different hats. I can't even remember all the ones they've got, but they have so many of those good escalation sketches where they keep trying to do to outdo each other. All right, doesn't matter. If you don't watch Key and Peele, you should. It's really sucks that it's not a show anymore. But that's beside the point. Anyway, like what I was saying is that when you come through here and you do like is leaf container, that implies to me that you could have just packed these values. So I think actually what we could do is like we could have is leaf container and we could have is leaf count, or actually just things that we unpack off the stack. So I think what we could do is say we don't actually need this, because when you actually do a cur stack value here, this doesn't need to occur anymore. I don't think. And I could be wrong about that, but I'm just going to say that I'm right, because maybe I can just claim rightness and not care. So what I'm thinking here is that, like, look, we actually load the cur stack value here if we're in a place that we know we're processing a node. But if we're not processing a node, in which case we're in here, then we don't actually ever need to do that, because the leaf index can just be the cur stack value, and then the one pass leaf index can just be that plus the leaf count, right? So those can actually be things that we just load off the stack. So in this case, we just run through the boxes like we do here. In this case, when we start popping things off the stack, we know that anything that we pushed on the stack here, we can identify whether or not it was a leaf container. And in fact, I guess that's one wrinkle in the whole plan that I hadn't been planning for here. So that's one bug I already just thought of. So when we're popping the cur stack values out, we need to know whether they're leaf containers or not. Now, you know what? I could just do that determination at the top of the routine. Like, so what we could do here is say, all right, the cur stack value is something that we pre-prepare that has all the information in that we need, right? So it's not actually that. We determine whether it's a leaf container, what the leaf count is, as unpacks on the cur stack value, which we do not use directly, right? And so then the part where we unpack the stack here is actually, this part is only going to unpack those two values. Of course, yeah, but then if... Grr, so hard to get this right. I guess I might as well do it, because I already have to unpack it there, right? It's like an alpaca. It unpacks. It gets unpacked. So yeah, I don't know. So anyway, as we roll through here, what I was trying to say is like, okay, so then there's like a leaf count value that you would unpack as well, right? That's going to be 0 here. And in fact, I guess one thing we could do is say we don't need his leaf container. We can just use leaf count at that point, right? So we could just say, look, there's a leaf count. If the leaf count is non-zero, that's how we know we're in the leaf. And then we start loading out. So in that case, we use the cur stack value as the leaf index, and we run through them all, right? When we're doing one of these, and we load these values up out of here, we need to do the unpack here, right? So we need to set the leaf count, and we need to set the... I think that's it, right? When we load one of these up, we just need to set the leaf count and the cur stack value. I think that's all we have. Yeah. So this is going to be a packed value. And then I'm just going to go ahead and do the unpacks here. So I'm going to have an unpack leaf count and an unpack node index here. We're going to take this packed value, and we're just going to say, like, look, we unpack these two things. And off we go, right? Up here, we're going to need some other stuff, because in addition to the cur stack, this one only needs the cur stack value and the leaf count. Those are the only two things it needs. This one needs, in addition to those, it needs the... it needs to actually load up this index. So we need to do an actual KD node load here, where in this case we're loading it off the cur stack value, and that's true. In this case, we're loading it off of the thing we just unpacked. So this is going to be an unpacked node index here, so that we can load up this thing that we're going to test, right? And then we just need to know which thing this is. So we need to know whether or not this is actually so this is a test node index, right? Oops. So off of the stack that we popped, we're going to see which node index we're working with. We're then going to look at that, and we also need to know the plain test pattern that we're going to use, right? So that needs to happen, right? Yes. So in this case, the test node index gets assigned back to current stack value, and also the leaf count gets unpacked. So we pull one off the stack. We see which one it is. We load the test pattern that we're going to need to use to see whether or not it's something we're going to actually test against. We take the KD tree node and we load it up so we can get its KD index. Yeah. So I guess another thing here is that this doesn't actually have to come from here. It could come from here if we wanted it to, actually. So we wouldn't actually have to pack that on, but I guess I don't see any reason not to at this point. But anyway, so we're going to load out the test node. We look at what the index is, and the start D, dir D, end D. We do the test, and off we go, right? Actually... one more wrinkle. So actually, no, that's not quite what we do. So when we push this on here, right, we're actually just going to push on this same one again, actually, right? Because we're testing the same node again, but just against the far side. So I think when we push this on the stack, what we're really doing is pushing on a different packed value, right? So we're doing like a pack value here where we're saying, oh, like, and I mean, I guess we can still do it this way, meaning we can still actually have that be encoded, the value we actually push. But it's actually going to be the same node again, is what it would be. And I guess you can't really do that now that I think about it, because you wouldn't want this to be loaded that way. So that's tricky, because that means the thing that we would have to push on the stack is much more complicated if we actually didn't want to have to load the KD node there, right? We could push the index. So in other words, this value could be on there. So that could definitely work. All of this would work. It's just this one thing that would cause the problem, right? And so the question is, do we make the stack 64-bit and push the KD plain D on there, right? Or is there something else we can do? So I don't see any other options. I don't know if you folks do. But it seems to me if we really wanted to do this where we don't have, where when we walk the stack, we don't have to load, which I think we wouldn't really want to if we could avoid it. I don't see any way of doing anything other than like this. So we would need a 64-bit stack in that case, where we have both a, one single floating point value. That's the plain D we need to test against to figure out whether we're going to do this side or not, right? And then we need the packed bits for first leaf index, first count, and the plain test pattern. Which easily fits in 32 bits. It's just like 1688 and you're done. But I don't know. Is it worth it? Is that the right decision? It's tough to say. Am I missing anything is the other question, because that's like, there's a lot of complexity here. Very simple set of routines. Actually, there's not much here, which is great. Like, the entire code for the KD tree walk is between there and there, right? So very little code, but does it actually do the right thing? Because it's so complex in your head, it's hard to think through. Is that actually a correct walk of the tree? You know what I mean? Like, is that actually right? And I guess the only thing, I mean, looking at it, it sure does feel right. The only thing I'm not sure about is when you actually push the other side on, if the other side was a leaf, does that work properly? So let's suppose the other side had a leaf count, and you came through here, and you did the test. This test is testing the parent, actually, not you. And then you would unpack the leaf count here if you were going to do it. So I think it does. This is incredibly small for a KD tree, but then again, it's probably actually still crappy. Like, I bet people have worked it out to much better than this. But it really looks like it doesn't do much. What do you think of this? Does this look right? I'm wondering if anyone on the stream thinks this looks right or not. It seems fun. But at this point, like, yeah, you know, I don't know. There needs to be a data structure named after Key and Peele. I totally agree with that. KP tree. Kind of like that idea. All right, if this turns out to be an interesting walk of the KD tree, then we're going to call it a KP tree after Key and Peele. All right, so this is what we need to actually build here, and so we just have to go through and do the encoding now. It means that our stack is not quite right. So if we look here at this box stack that we've got, that's not going to do it. It's got to actually be U64. And so, again, I'm going to actually just create a new one here. That's going to be the KD stack, and we're going to use that instead. Again, we'll clean all this up once we actually verify that this is something we want, because this is all experimental code, so I don't want to remove the other code until we verify that we're actually faster and better. If we're not, then we just shouldn't be doing any of this stuff, right? It was a good mental exercise, but we don't know that it actually helps, so, you know, we need to verify that first. So we're going to do the KD stack there, and then the KD stack here. And when we're actually doing these unpacks, these are 64s now. And this here needs to pack the plain D in there. So this is going to be like a pack node, pack KD stack, where we pass these two in. And I think that's what we're doing. I think that's what we're doing for the encode and decode side of this, right? So then I'm just going to drop this crap in the top. Actually, I guess I'll drop it at the top of this particular routine as well. So like right here, I'll do a pack KD stack. And I'll do all the unpacks as well. And this is just, this is just to make sure that we can easily modify these things and see them all happening in the same place, because otherwise, if I inlined all of the packing and unpacking, that might be a little bit squinky, right? Okay, so what we want to do here is have these unpacks work on probably the low 32-bit values so that we can actually run them. Well, I don't actually know that that's true. Forget what I said. So this is going to be the plain D, and this is going to be the like packed side value. And so when we do packed KD stack here, what we're actually doing is we're just saying, look, we're going to convert excuse me. We're going to convert the plain D value into a 64-bit value that we can shift up. And we're going to, or maybe we'll just do the packed side value that way. I don't know which one we should slide to the high side. But we basically want to do this. So we want to move the plain D up to the high 32 bits, and we want to move the packed side, or the packed side in. Now, excuse me. The problem is we want it to treat this thing as if it's a U32 value. So what we really want here is more like this. So we want it to load this thing as if it's a U32 value, even though it's not. And then we want to convert it to a U64 value to shift it up, which is really wonky. Personally, I hate the way C does this stuff. I've never liked any of this stuff. And C++ is like even worse. What you want to do is say, look, load this thing into a 64-bit register, slide it up 32 bits, and OR the thing in. Okay, it's like 3 instructions. Why does it look like this ridiculous garbage, right? And again, it's just because the priorities in a language like C++ are completely backwards. But we'll work it out and get something that looks okay. For now, we just need to do some unpacks in here. So we know we're getting a 64-bit value in here, and we know that these things need to come out for smaller values. So I'm just going to have the downcasts in here. Isn't there one more thing we need to unpack? Is it really just 2 things? Is it just the node index and leaf count? I guess just another. Wow, that's. No, the plain D, the plain D, the plain D, the test pattern. Yeah. I was like, there's more stuff. What are we talking about? I'm like, that's way too few things. All right, so we've got the leaf count and the node index, then we've got the test pattern, the plain D, and the KD index. Now, the plain D is like totally separate because it's literally just the thing shifted down, right? And again, like unpacking this thing, I don't even know how we're going to do this because it just doesn't work in C correctly. We may have to use like a struct to unpack this, but I'm worried about doing that it won't know what to do. You know what I'm saying? Yeah, I don't know. So again, this is me just trying to give the compiler something that it will do the right thing with, which shouldn't be a thing, but it's what you often end up having to do for no reason. Okay, so in here, what we actually want to do is we want to take this pack value, which is U64, and we want to be able to access it as if it was an F32, and we want the high F32, right? So what I want to do here is say, like, all right, pretend this is an F32 star, and then I want you to give me, out of that F32 star, I want you to give me the next one, right? Like, I want you to give me the high F32, not the low F32. I have no idea if that is something that the compiler will generate the right code for. In fact, I have no idea if it's going to generate the right code for any of this. Maybe we should actually have a struct for it. I'm just really, really worried because we've seen MSVC not be able to push structs on a stack at all. So it kind of needs to be a U64, but I don't know. Okay, so here's a thought. Maybe. So one thing I could do here is I could introduce a struct that's like this. You know what I'm saying? And so I could do something like this, where we just say, when we have a packed one of these, like, we're just going to treat it as this thing and see if the compiler understands that. So, for example, I could say, look, this is going to be one of these, right? So we take the address of the pack thing we're given, we treat it as if it's a KD stack pack. Maybe that helps the compiler, maybe it doesn't. I honestly have no idea if it will or if it won't. And then off of that, we just get the D value, right? And then here we do the bits values equivalently. and like I said, I just have no idea. I mean, like I said, this stuff is so easy in assembly language, it's a joke. And yet in C, which is ostensibly supposed to be easier to program, it's an absolute nightmare, if that makes sense. And it just, yeah, I mean, it's just stupid. It's the only way you can say it, really. Okay. So assuming we unpack that, and maybe the other thing I can do here is introduce a helper macro that's just like unpack, and it's just this. So the only thing this thing does is it takes one of these like casts there and gives it back to you. So you can just do like, you know, this is unpack the pack value and get the D value. This is unpack pack value and get the bits value. And so for each of these things, we need some way of actually producing, you know, the correct set of bits out of the pack that we want. And so that's the last thing that we need to actually put in here. So in order to do the unpack, or in order to get the correct bits, so we need to just assign each of them a location, right? And so for each of these, we just need to like shift and mask it to the part we actually care about. So the plain test pattern, the KD index is like 0, 1, or 2. So this is 2 bits, right? This is 4 bits, so that's 6 bits. This is 8 bits, and this is 16 bits, right? So this is like, these two make 8 bits together. Well, they make 6, but rounded up to 8. These two make 8 bits. This is 8 bits, and this is 16 bits. And that's our 32. Right? Okay, so let's suppose that the way we want to do this is the node index is the bottom 16. Right? The leaf count is the next 8 from there. So like this. Maybe. The KD, oops. No, that's right. The plain test pattern is going to be I guess we'll just say the plain test pattern is the next 4, and then the KD index is the top. Seem right? I don't know if that's the right packing or not. But anyway, so if we actually go ahead and say 32 minus 4, right? So it's going to be what, 28? So if we want to grab the KD index, we just shift down those 28 bits. If we want to grab the plain test pattern, we just grab the 24-bit version and mask off. All right, so this is 16 bits, this is 8 bits, this is 4 bits, and this is actually not 4-bit. We're giving it 4 bits, but it actually only needs 2, so we actually have 2 additional bits in there, right? I'm going to call that done, and we'll see. In here, we need to pack a KD stack value on here for the root box. To start with. And in order to do that, we need to have, so the way we're going to have to start to make the root box work here is actually, we're not really going to want a root box index. We're going to want like a root box value. So inside the lighting code here, like we're actually going to want like root box value. It's just a thing set up to like start the routine, right? And I guess it's technically just it's a leaf count of 0 with a box cur stack that we pull, right? Which I guess is the same. I mean, we could just use this. We can just use the root box index. Where is that from? It's here. So I guess we can just still use the same value. That's fine. So we know it doesn't have a leaf count, so we know we're going to jump right down to here. We're going to load the cur stack value out, and then we're going to start like processing that box, right? Now we need to fix all our macros, which are probably all broken. This is supposed to be unpack capital, like so. And for all of these, after we're done with it, we probably also want to just undef these macros. Okay. And that is maybe the routine. Unpack plain test pattern is a problem apparently because of why exactly? Oh, yeah. So well, no, that seems right. What's the problem? Is it because we have an unbalanced parentheses here? Let me take a look. So unpack pack bits, then we've got this, then we got that. Seems right for this one. And seems right for this one. What's the problem? So we've got that enclosed. We've got that enclosed. Ah, yes. We need one more there. Yeah, and this one, shouldn't this one need it too? Yeah. It says we've got a right shift by too much for data loss. Does that mean I'm casting in the wrong place there? I might be. Yeah, this one needs one more too. We're going to have to check all those. Okay. So here where we've got the ray direction, I'm assuming that's just ray D, right? Yeah. Unpack leaf count is probably a little bit borked. So there's that bracket, there's this bracket. Am I right? So there, and there. Okay. And then finally, these are just lowercase d now. And so the KD plain D value needs to be lofted up to do to a 4x to do that subtract. Now, interestingly enough, we don't really need to do this 4 wide. It's just that's the only floating point unit we have. So I guess we're going to do it 4 wide just because why not, right? Oops. So yeah. Now pack KD stack. I guess I'm not sure what else to do here other than I guess this cast needs to be, the problem I think here is that this needs to be like isolated in here. This needs to get cast to U64 first, then shifted up before, so it's just a case of more parentheses. Again, this is so annoying. It should just be assembly language. Like, it's so annoying. Anyway. This is supposed to be dir-D. Thank you, compiler. That was a good catch. All right. So now I think we have the full sketch of the routine. It's all done. And so the only thing we really have to do now is build it, right? And that maybe waits for tomorrow. But that looks like roughly what we need to do. And we should be able to take a look to see if the code that was generated for this these unpacks were sane or not. And I don't know what we're going to do about that if they're not. We could split the U64 into 2 values first using a U32 split and then pull the plain D out that way. So we may want to hand code that in a little bit anyway. We'll see. But we need to like analyze that first either way, if that makes sense. But I think we're good. I think that's pretty good. I don't know what I should do now. Maybe I should go to questions, or maybe I should start the split box modifications. And I'm not sure exactly how I want to do that, but what I think I might do is just make something that reads the old tree and writes the new tree, or something like that for testing purposes. I'm not sure. But yeah, like what you'd want to do here is you'd want to say, okay, anytime, like, I think we probably just want a totally different split box call. because we're going to do the same testing, but we're not going to write the same kind of values. So what we're actually going to be doing is on either side, we're going to look to see whether or not we split the child. And if we do split the child, then we don't write a new index, right, for that thing. And so, yeah. So I think I'm going to go to the Q&A, and we'll take a look at building it. We'll take a look at building it tomorrow. That'll be our tomorrow job. That's a tomorrow job. And then I think we're pretty home free on the KD stuff. It's just going to be a big debugging nightmare. But we're home free on the implementation side. Because the split box quality does everything we want. We just have to reorganize it a little bit. The hair is getting so big. Like, it's insane how much hair there is now. I know someone was saying nice hair. It's crazy. You probably can't even see just how much. It's kind of like flattened out at the moment. But like if you actually poof it out, like it's insane. How's the C course coming? It's coming. It's a lot of work, but it's coming. What about writing a plugin for forecoder that highlights unclosed parentheses? So yeah, I already did all that, but then I moved all the code to my own editor when I did that jump. So I just haven't gotten around to like. I only use this editor setup on stream now that you're looking at here, and I just haven't been motivated to clean it up. I should at some point, but forecoder already can do that. Like if you want it to. Stay fire nice. Oh, yes. That's a good point. I said it wrong, didn't I? Yeah. Looks like you can recover the Milton temp file from app data and Milton Paint data. Yeah, only probably if you haven't started a new one. That seems like a really bad way for this program to work. I would strongly recommend changing that if anyone cares. Like, it should never get rid of the old canvas. Like, just move it to a different file, right? Because I thought it was saving it to that file. Like, I didn't understand that it wasn't ever saving my thing. Like, that was not something I understood at all. Looks like you can recover the Milton temp file. Yeah. Oh, sorry. No, that wrong. Where can I get info about the C course? Just add yourself to the mailing list. So if you go to mollyrocket.com/follow, put your address in here. As soon as it is on early access on Steam, I will send out a mail, so everyone will get notified when you can actually purchase it. but it is not up yet. But add yourself to MallyRocket.com/follow, and you'll get a mail when it's ready. Today, John said that deferred rendering is a bad idea. Why? You would have to ask John. Deferred rendering is a bad idea. I don't know. Deferred rendering is a good idea, isn't it? I mean, it's not always appropriate. Like, for the most part, I would say that, like, deferred rendering is a technique that you use when you have favorable conditions for it, right? But I don't know why anyone would say it's a bad idea. It's a good idea. It may not always be appropriate to your particular task that you're doing for rendering, but that doesn't really make it a bad idea. It's possible if John literally said it's just a bad idea across the board, like it should never be used, that seems confusing. But what he may have just meant is it's not appropriate for something he was talking about. Didn't he just mean that almost no one uses deferred rendering anymore? Is that actually true? I don't know. I don't know if anyone's... In fact, what's the latest one of these? So, like... I mean, this is deferred rendering right here. Right? Unless I'm misreading that. I'm just reading this really quickly, so it's hard to say for sure. This is deferred rendering right here. This is deferred rendering right here. Like, does anyone not use deferred rendering would be the way I would say it? Like... But they do that, right? I mean, this is what that is what this is. Like, this is how these renderers work. They write the diffuse channel, the normal channel, the specular channel, irradiance channel, and then they combine those later, right? I mean, that is how that works. Maybe he was talking about some other technique. I'm not sure what it is necessarily. But, like, maybe this is not... I mean, he's calling it deferred rendering, the person who's doing the breakdown. But, I mean, I don't know. So, I don't know. I guess I would say, like, yeah, I'd ask John who he thinks isn't using deferred rendering among the main graphics engines. Because I think they're all using it. I think maybe not, like, Unity or something, because, you know, it's not really a high-end kind of thing, but, like, I would assume that, like, everyone else is. This is not an actual whole thing of Unreal, so this is only, I guess, the post pass. But I mean, I just thought everyone does it. Like, I don't see how you would get away with not using it most of the time in a modern high-end rendering. I'm not sure how you wouldn't use deferred, right? But so yeah, I would say just ask John who he thought was not using it, because everyone does it, right? If you're high end, I think. I mean, maybe I'm wrong. Maybe I don't understand what he means or what they mean. I don't know. But that would be, I would say that's very counter to how I think about graphics. You oftentimes have multiple deferred steps. On high end. On low end, you probably don't want to do that because, like, if you're a 2D thing or whatever, you probably don't want to be doing a lot of deferred because you're trying to run on lower end hardware and stuff like that or something. I don't know. Could you explain the 00111 KD side testing again? Yeah, and again, when these are just my guesses about how to do this right, because we haven't looked. Like I said on Handmade here, I always try to implement something once myself to demonstrate how I would go about doing it if I couldn't just go cheat. But we'll probably eventually go look at how other people are doing KD walks and see, because it's a very well-studied problem, and we should be able to get some extra stuff there. But all I was saying is, let's suppose here is our KD split plane, and here is our ray origin. We know that the ray origin is fixed. So all 4 rays are coming from the same origin, because we use this to gather light from a light probe, and the light probe is in one place when we're gathering it. So we've got a fixed ray origin, but several KDs, ray Ds rather. So the ray D value, which is this, there's 4 of them. So this is a SIMD lane that's 4 wide, right? So there's, it's packed. It's like 4 or, 3, 2, 1, 0, right? And we know that we've got 3 times that because we've got X, Y, and Z. So we've got, X, Y, and Z. So we basically have like 3 registers or an array with 3 values in it. And each value is 4 wide, right? So this is, this is 3x, this is 2x, this is 1x, this is 0x, this is 3y, this is 2y, right? And each of these is 128 bits wide, 16 bytes, right? And that's because each of these is 4. So that's the data we're working with. My hypothesis for the KD tree, and I have no idea if this is correct, this is just kind of what I whimsically came to in my head after trying to look at the problem a little bit on stream, is that we know we can always classify the ray origin fairly trivially by just going, look, let's load the X, Y, or Z, whichever one the KD split plane is splitting, because we know that it only splits one dimension at a time. So we load whichever one of those it's actually splitting, and then we can say, all right, take the value and subtract the plane D value, right? That will give us a positive or negative value depending on which side it's on. And we know that the ray origin is the same. So each of these values in the ray origin is the same. The ray D value is different, but the ray origin is the same. So all we have to do is just look at one sign bit from any of these 4. And so that's what we do. We just look at this low sign bit. We just look at AND1, and that tells us whether we're on the positive or negative side when we start, right? Now then what we know is we're going to recurse down that side. So whichever side the origin's on, that's the side we're going to do. But there's another side over here, right? And there's stuff over here because it was a split plane, so we know that there's things on this side. So the question is, after we test what's on this side, do we need to test what's on this side? And my argument was, look, if I add the current ray T value to ray origin plus the T value times D, I'm going to get the location of each of these rays as its current best hit. So it's either going to be here, 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 or here, depending on which one of the four rays you were talking about. But I'm going to get 4 values that tell me where the ray would end, right? And what I want to know is, are any of them past the split plane? Because if none of them were, if it was like here, here, and here, then I just don't need to look at this side, right? Why bother? Like, I don't need to look at the other side of the KD tree because I know that I can't ever get to the other side of the KD tree. So just don't bother. So what's that going to look like? Well, when I actually do this, origin plus t times direction, right? I'm going to get out 4 values that have a sign. And then I subtract the plane d value, right? I'm going to get out 4 signs again, just like I got out when I did the origin, and I only needed 1 in the case of the origin because I know that's always the same. But for this, they're going to be 4 different values. So I've got 4 sign values. All I need to know to determine whether to go down this side of the tree or not is, are any of them the wrong value? So if I was on the positive side and I want to know, do I go to the negative side, I just look, are all of the signs positive? If they are, I don't have to look at the negative sign. If any of them are negative, I have to still go down it, right? So that's where you get that not equal to. You just say, look, if it's not equal to the exact mask I'm looking for, I do have to descend, right? And again, I'm sorry if I typed it in wrong. We haven't debugged this, so I'm not even claiming that this code is correct. I'm just walking you through what my idea was, right? So here what you can see is I said, look, if we're going to take out the sign values, that's what move mask PS will do. So this is going to take out the sign values. We're then going to look and say, if the sign values are not exactly what I expect them to be for an early out, then I have to walk the far side of the tree. Does that make sense? Yes, what is the initial t value? The initial t value is the furthest you want to go before you consider there to be no hit. So basically what we would set that to is the lighting region. We just set it to like, and right now we kind of just set it arbitrarily, but if we wanted to be completely conservative, we could set it to the total maximum diagonal distance from one end of that volume to the other. And we know that we can't ever have a hit that's further than that because that's the entire geometry. We don't have any geometry that is further apart than that, right? So we can do that, but it doesn't really matter. Just the initial t value is whatever you wish to pick as the furthest you can consider a hit before you just say, look, we know we can't have hits that are further than that because our geometry is now out. We're not there anymore, right? Someone also mentioned Learn OpenGL. This tutorial is about deferred rendering, and he said, be careful who you learn from. Is it deferred rendering has some pitfalls or something bad that only pro programmers know about? Again, I'm sorry, but I do not know what he means. You can't ask me questions about what John means because I don't know what John means. Everyone uses deferred rendering as far as I know. I don't know anyone who doesn't use deferred rendering, but I'm not a rendering person. So I don't know. You can theoretically go full forward using clustered shading. Yeah, but they don't. Like Doom uses clustered shading, but they still defer, right? I mean, that's exactly what this was, if I remember correctly. Like, didn't we just have this up on the screen? So Doom is a clustered renderer. It uses a screen-aligned, like, voxel basically grid to break the screen up into sections. And then when they go to render, I mean, like, here you go. I think they still use G buffers. So I don't know. I mean, it's possible that maybe you don't have to use them if you do some stuff they didn't do yet or didn't have time to do, and maybe now they don't. Like maybe they use in the new Doom renderer, which I don't know anything about. Like I haven't seen a study of them. Maybe they now no longer do defer any of the values, but I mean, at least the last time, this is the only clustered renderer I know of that's like a highly optimized cluster renderer. I don't know who else does highly optimized cluster rendering. There probably are some people who do, but this still used a deferred pass on 2 of 3 of the components, right? So I don't know. I mean, it is true that people still use a depth prepass as well. Like you can see all of them use a depth prepass because it's pretty much always the case that people do a depth prepass, right? So you also do a depth prepass, but that doesn't mean you're not deferring anything. Oh, so there's the new Call of Duty. Which Call of Duty does Z-binning or clustered rendering? I mean, you know, whatever they want to call it. Which Call of Duty does it? I mean, not that it matters because it doesn't look like we've got a graphics study of it there, but anyway. So Call of Duty Infinite Warfare, which is whatever that is. All right, so here's the Z-binning. Whoa. Yeah, you're right. That's a lot crazier. Yeah. So clustered renderer still, but yeah, that's an interesting cluster thing. Yikes. All right. All right. I would agree. This looks pretty nutso. This looks kind of ridiculous. Is this really a good idea, though? I mean, man. All right. Well, this has nothing to do with deferred or not, but just like, man, that is some much more nutso binning than the normal one. I mean, when you say it's faster, but how do you know it's faster? You sure it's faster than the one that they use in Doom? I mean, all right. You know, I don't know. Anyway, I don't know. The end of the story is just, I have no idea what John meant by that, but you should ask him, not me, because I don't know what he means when he says things. He knows what he means when he says things, so I can't help you. What I can tell you is, as far as I know, deferred rendering is still used almost everywhere in high-end engines. But that's all I know. So that's what I've got for you. I'm going to go ahead and wrap it up. Oh, God. So you actually did what, the crazy renderer in your engine too? The crazy Call of Duty one? That's, whew. All right. Well, good for you. I mean, that did look pretty nuts, but the problem is we can't ask him because he's angry about it. Okay. Well, that's fair too. Then don't ask John about it. Just go figure it out yourself. Right? I mean, you know what it is now. You can go read like those graphics breakdowns and you know what it does. And you can figure out whether it's good or bad for what you're doing. You know, step up to the plate. You don't need John to tell you one way or another, right? So I think Carmack said deferred rendering doesn't work well in VR. Like, who cares about VR? VR is just totally such a waste of everyone's time, and so much money got poured into it, and no one cares. Like, nobody cares. Exactly like I knew no one would care. It was just a gigantic way to set literally billions of dollars on fire and never see it again. So, yeah, great. Anyway, I'm gonna wrap it up. Yeah, like I've said this many times, like AR is something that will probably catch on. VR, no one will ever care about, ever. It's never going to be something people care about. It's only AR, right? It's only once you get it to so people can still feel like they're actually still in their real tangible environment. Like it's just not the case that like people are actually still social. They don't want to feel like they've been completely alienated from the real world like that. I mean, if they were, they would all love coronavirus. They would love being locked at home without ever being able to see the real world ever, right? But that's not the case. Like, very few people actually want that. And while it's true that it's a good little, like, fun, crazy thing to do once in a while, like, oh, that was cool. Like, I put on the VR goggles and I was down with the whales for a minute. Like, sure. But that is not a revolution. That's just, it's like the Nintendo Wii. It's a little thing you do once, and some friends come over and you try it one time, and oh, well, that was weird, and then you never think about it again, right? So it's just like, VR not necessary. It just, we shouldn't have bothered. It's a necessary step to AR, perhaps, but say that, and that's what you're doing. You're just going down the road to AR until you get there. It doesn't matter. So, you know, call me when you're at AR, and then I agree there's probably people are going to start liking that. Because when you can just put on like, glasses like I'm wearing now, and you can actually just see extra stuff augmented into the world, that seems like people will use that. Like they used a smartphone, So, anyway. That's it for today. Thank you for joining me for this episode of Handmade Hero. It's been a pleasure coding with you as always. If you want to follow along the series at home, you can always go to handmadehero.org and pre-order the game. It comes with the source code, so you can follow along with it. You can go modify the split box routine before tomorrow. Try to beat me to it. Everything is there. We just have to reorganize the data. So no real new thing happening, but give it a shot. Also, we got a Kickstarter going on right now for our comic. It already succeeded, but we want to try and get as many people comics as we can. So please check it out. We're going to add a stretch goal in there, another stretch goal, because I think it hit all the stretch goals already, or almost did. So we're going to add another stretch goal in there soon, too. So check it out. And, yeah, if you like cats, or you like space, or you like cats in space, you should check it out. I'll be back here tomorrow when I'll write that split box routine. And then we can start seeing... First of all, debugging this thing. Does it actually work? Like, did I miss a case somewhere? Highly likely. But then we can look, did it help? Does reducing those ops, the number of ops, does that help us? And we don't know. So we'll see. Hope to see you back here for that. Till then, have fun programming, everyone. And I'll see you on the internet. Take it easy, everybody.